Hello everybody, I hope you can hear me. I'm here to talk a little bit about the project we are doing right now. So it's not finished, it's still in progress because there is a lot of buildings that have to be built. And I think it's interesting because it's really the newest one and it's a little bit challenging. And what I want to share to you is the ideas behind the design of the whole network, and not primarily which switches we used, which technology we used, but what our ideas were designing it. So first of all, I want to ask you, who actively designed the network of all of you? A few. So these people, they know a lot about problems, about challenges, about things that are planned and that don't work out. That's the reality. A plan is never ever finished, and usually you have to adjust to it all the time. So this project is about industrial switching. Industrial switching in that case doesn't mean that we're just doing for an industry. Basically, we do it with a certain set of tools. Especially the environmental parameters are quite challenging in most of these projects. So we need switches that can withstand something like 80 degrees plus, which is really hard. It's way easier to build equipment that can work at minus 20 or minus 40 degrees, because heating is quite easy, but cooling can be an actual challenge. Everybody who designed the data center knows that cooling is a real challenge, and it's also very, very costly. So this is the basic project. The basic project is a ropeway. A ropeway is, in my opinion, very cool technology for public transport. These two pictures are not the project, because it's not finished. They're still building the buildings, they're building the pylons. So I can't show you anything but a few empty concrete blocks. The left one is from La Paz, Bolivia, where they were facing the same problem basically than the project in Haifa. A lot of mountains, no space for roads, and no real way to build a subway or a railway or an efficient public transport system. The other building is from, I think it's Dubai or United Arab Emirates. So in these projects, basically what they build is a cable car. The cable car is designed in the way that it's split up in sections. Israel used 6 stations, so it's 6 sections. You enter at the first station, and you can stay in the car for the whole time. So it changes between the ropes automatically on the stations, which is quite a challenge in itself to make that work, to get people out, get people in. It's really an interesting technology behind it. So the cables are mounted on 36 pylons. Each of these pylons needs surveillance. So if you look at the right picture, you can see there are rollers on top of the pylons that hold the cable. Sometimes it happens that the cable moves out of the roller. In that case, it has to shut down immediately, because that's really dangerous. It shouldn't be out of that roller anyway. So the company that designs the ropeways has a system that is actively monitoring the position of the cable. Now for the problem. That's not always working. So they have a lot of false alarms. Could be that a bird is interfering with the sensors. So they need a way to actively check if this is true what the monitor says. So that's why on each pylon there are several cameras that are pointed to the rollers so that they can actively monitor visually. If you have 36 pylons, 4 cameras on each pylon, this could be a challenge just by looking at all those cameras. So usually they're shut off. Just in case the displacement monitoring kicks in, the camera is switched on and it gets displayed on the operator's desk so he can decide, is it necessary to shut down the ropeway, or can they actively stay in operation. So that's not enough. To entertain the guests, you need wireless access. So on each of the pylons and in the stations, there are access points. These access points supply wireless access to all the cabins. So you can easily look at your emails or do whatever you want. These roaming between the access points is a challenge in itself. Fortunately, I'm not the one who has to solve it. I just have to solve the layer 2 connectivity, which is the easy part in that case. So we were facing the challenge that it's quite a long chain of devices. And if you ever designed a spanning tree network, which is the standard approach to doing a little bit of redundancy, you know, in that situation, no way that this works. And if it works, it will take almost forever to reconfigure. So we had to change our approach. This was the first thing we thought about. Very, very easy. So I don't trust in too many details on these drawings. So we were thinking about interweaving 2 rings to get the whole connectivity. So the red ring is on the pylons, so there's a fiber cable that connects in all the pylons. And the blue ring is just connecting the stations. So the blue ring is basically the layer 2 connectivity for the stations, and the red ring is layer 2 connectivity for all the pylons. That would work, actually, but it's not a really good solution. If A and F, the station switches, fail at the same time, there is no communication anymore. So you don't have access to any of the pylons. If 2 pylons, let's say number 4 and number 16, fail, you lose a lot of your network immediately. So the better idea was to do a little bit of segmentation on that. And for that, CTS developed a nice technology. It's called chain. The fast ring we're using is a proprietary ring technology. It's partly similar to ERPS, but way simpler. So it's not designed to replace ERPS. It is designed to have a simple working solution that's very easy to configure. So if you really want to configure something like the blue ring on all these devices, it's, if you know what to do, 20 minutes maximum, and it's up and running. No problem. If you don't know what to do, it's 5 minutes more. Because you have to figure it out for one switch. All the other ones are basically the same thing. The nice thing here is the chains. The chains were designed with the idea in mind that sometimes a ring is not possible. Especially when we started to designing it, we didn't know if the customer would actually choose our switches. So we cannot rely on technology that we use in our switches if we don't have them. That's where the chain kicks in. This is the beauty of this chain solution, which I really like, because it's very, very flexible. It gives you the same basic redundancy features of a ring, but without being a ring, and without being in need to interact with the other devices. So basically, you could use extreme switches for the stations, no problem at all, and just connect the chains to it and it would work just the same. So the chain is, in my opinion, even easier to configure than a ring. It has just let's say three different things that you have to decide. Whether it's a tail port, a head port, or a member port. Very easy. So the head port in this case is connected to A, the tail port is connected to B, and all other ports in between are member ports. That's it. You're ready. The fun now is the head port, if it's connected and it detects a link to another device, it says, okay, I'm up, I'm running, I'm working. The tail port just checks if it can reach the head port. If it reaches the head port, then the tail port switches itself off. So whenever there is a break in the cable between, the tail port cannot reach the head port, and within 50 milliseconds, it switches on, and traffic is running again, just in the other direction. So for a layer 2 network, this is a very easy solution, and very fast. In the whole process of designing it, we were thinking about how fast it could work, and how many devices we could put in. So my colleagues in Taiwan set up 200 switches. It works within 50 milliseconds. So usually you don't see even an interruption in a video stream, or if you stream music or use a phone, voice over IP stream, there's no way that you can detect it. You can measure it, easy, but you can't see it, provided that you're using fiber ports. For all these fast redundant technologies, never ever use a copper port. So if you really want fast switching, you have to use a fiber port, because the link detection on a copper port takes about 1 second. So no matter how fast your switch could react, it cannot be faster than the link detection. And if that is 1 second, you lose at least 1 or 2 pings. So the nice thing here is that it's very, very easy to configure, very fast, and it works without the need of an additional protocol, like ERPS. So if you ever configured an ERPS ring, it's a real pain to configure it. And in case something breaks, you have to replace that switch with exactly the same configuration. If you just plug in the SFPs the wrong way, it won't work. And it takes quite a long time to troubleshoot that. Here it simply doesn't matter. You just plug it in, it works. So basically we are just using 3 types of equipment. This is a industrial type switch. Very small. It fits on a DIN rail. It's DC powered, redundant DC powered. So you can just put it into a standard box and it will work. Everything else you can see in the data sheet. So I don't think it does make a lot of sense to tell you what's already written there or what's in the data sheet. This is one of the nicer things that were also a key part in the decision there. This is K21 surge protection for lightning strikes. So K21 is up to 6 kilovolts, which seems to be quite a lot, but if you look at the voltage of a real lightning, it's nothing. So a direct hit, no way any device can really protect itself against it. This is just for indirect hits. If the lightning directly hits the camera, you see a stream of molten copper running down. So there's no real way to solve that. But for indirect hits, it's a very, very good protection. 6 kilovolts is quite a lot for an indirect hit. So under normal circumstances, it will withstand quite a lot of surge. No direct hits. That's simply not possible. EPS, this was the switch they finally chose for the stations. It's basically a 24-port PoE switch with combo ports for fiber uplinks. And we implemented the fast string technology in that switch so we can directly interact with our industrial line. So in a lot of industrial solutions with proprietary fast switching protocols, it's just among that solution, and you cannot get out of that world. So you would have to place another switch there, which basically makes it a little bit more complicated. It's more cost, and it's also more likely to fail because every single switch adds a possible source of failure. That's it. I'm really fast, I guess. So I don't keep you from lunch. There's just one thing I want to share with you. What I didn't say is that we are using single fiber optics in that project. And this is for redundancy. Now, everybody says to me, why? Because if the single fiber breaks, everything is down. The trick is, you have 4, 8, 12 fibers, something like this. If you use 2 fibers and 1 fiber breaks, what happens? Your link is down anyway. So if you use just a single fiber, you effectively have half the chance that it actually breaks. So single fiber optics is quite a good idea, and as the prices drop so far, it's not really a price problem anymore. It's just a few dollars, euros, whatever, that it's more expensive, and it's well worth because it's very, very easy to set up. It saves a lot of fiber capacity, and it's more reliable. Thank you.